Okay, let's get straight to the point here. We are working on a linear programming problem. Um, Here you have bakery 1 and 2. This is a generic case, right? And there's a supplier. In this case, the supplier is the bakery. You have two bakeries, 1 and 2, and it supplies to a certain warehouse. Okay, and you have warehouse 3 and 4, right? And then this warehouse will supply um, to the stores. Okay, in this case, the stores are restaurants. Restaurants 5, 6, and 7. So we're going to use index 1, 2 for or index I, which is equal to 1 and 2 for the bakery, J, which has values 3 and 4 for the warehouse, and K has values 5, 6, and 7. Okay. Now, what we want to do is that we want to determine how to move the goods from 1 and 2 going to 5, 6, and 7 at the minimum cost. Okay, so that's what we're gonna do. We want to minimize the cost of shipping the goods. In this case, the goods is like I don't know, cake slices. Yeah, it's cakes, slices of cakes. Okay, so from bakeries to the warehouse, and from warehouse to the restaurants. Okay, so the following table here are just the costs. Okay, so the cost that you see here, we put it in the table. Okay, so the okay, so this is like, the cost from 1 and 2 going to 3 and 4, and the cost from 3 and 4 going to restaurants 5 and 6, 5, 6, and 7. Notice that since we are minimizing cost, okay, I want to ingeniously put away so that the computer will not select 1 going to 4. Okay, so you see here in the picture here that 1 going to 4 is not possible. So what I would do is put a prohibitively high cost. Okay, so prohibitively high cost from bakery 1 going to warehouse 4, right? So 1 to 4 is not going to be possible, but I'm gonna make it possible in my model. It's just that the cost is very high. Okay, the same thing with moving goods from 4 to 5. Okay, 4 to 5 is not possible here in this diagram. I'm gonna again make it possible, but just simply put a prohibitively high cost. Remember that we're going to minimize the cost, so we want the computer to not select this route for going to 5. And then 3 going to 7 is also not possible, so we don't want the computer to not select that route. Alright, so our decision variables are, okay, let me just delete this one first. Yeah. Okay. Our decision variables is that xij, this is like the number of slices that goes from I to j. Yij is the number of slices that goes from j to k. Okay, yjk. Right, so these are all like integers. Okay, they should be integers, and we want to minimize the cost. Okay, obviously the cost will be like the number of slices times the cost of delivery, like per unit. These are like per unit delivery costs. Okay, so we're going to form that by using sum product functions. So sum product of xij times cij, right? So this is the xij and this is the cij, yeah, plus the sum product of yij times yjk times cjk. This is like the yjk here. Okay, how many from j to k? That's yjk, and then cjk is the unit cost from j to k. Yeah. So we are going to do that. See, this two sum product functions does it. Okay. Right. So, oops. Right. So that's the two sum product functions that we have in there that takes care of it. Now for the constraints. Okay, so we see here that those that come out of 1 and 2 must go into 3 and 4. Yeah, and those that goes out of 3 and 4 must go to 5, 6, and 7. So we could actually just simply focus on 3 and 4. What goes into 3 and 4 must come out to 5, 6, and 7. So, you know, okay, so let's put the constraint first. Okay, according to this problem, 1 and 2 have 1,000 and 1,100 available units. Okay, so that means that what goes out of 1 and 2 must be 1,000 and 1,100 respectively. So these are those constraints in here, right? X1J, right? J goes from 3 to 4. From 1 going to J, right? And then from 2 going to J, where J is 3 and 4. Now, so how do you do that? So we say the total of those coming out of 1. This is like the total of coming out of 1, right? Has to be less than or equal to 1,000. And the total coming out of 2, and that's going to be this, okay, must be less than or equal to 1,100. Next. Okay, so in this problem, warehouse 3 has 200 units available already, yeah, in its inventory. Okay, so those that come in 3 plus the 200 that's already available must come out of 3. Okay, must come out to 3 going to 5, 6, and 7. So how do we say that? So we say this: those that goes into 3, right? Xi3, you know, where I goes from 1 and 2, yeah, plus the 200 is available must be greater or equal to those coming out of 3, right? From 3 to K, yeah. All right, so we say here sum of xi3 plus 200. Okay, so sum of xi3. Okay, so sum of xi3. This is like, those are things that are coming into 3 plus the 200 that they have, right? Must be, okay, sum of y3. Okay, so those coming out of 3. So this is those coming out of 3. That's the sum of these three numbers here. Okay. Now this constraint here says those coming into 4 must be greater or equal to those coming out of 4, right? So the coming into 4 is this. Okay, see that's one being highlighted. Okay, going out of 4. Okay, so it's that thing. Right. Now this next constraints here are like the demand constraints, you know, so 5, 6, 7 of certain demands. Okay, so 5 needs 800, restaurant 6 needs 900, restaurant 7 needs 500. So this means that what comes into 5 must be greater than or equal to 800. What comes into 9, into 6 must be greater than or equal to 900. Okay, so what comes into 7, okay, so what comes into 5, 6, and 7, this is 5. So this is like the sum of those that goes into 5. Okay, now this is like, if you highlight this is the sum that goes down into 6. Okay, right. Now obviously we have here that, you know, xij and yjk must be integers. Now let's put the solver here. So we go with data, we say data solver. Okay, and then we put this thing. So first off, we want to minimize the cost. Okay, so the cost here is B28. So we gotta look at the cost. Okay, point to the cost here. That's the cost. Okay, the one with the formula and sum product. And you have to minimize this. And you know what, I'm gonna reset this. And I'm gonna put it again. So you have to do it. Okay. So here we want to minimize the cost. This is the cost. and these are the let's make this bigger, and these are the decision variables. You highlight the xij, and then you highlight the yjk. Select the yjk. So you put a comma, right? And then the constraints. The first constraint, we go through each of this, okay? The first constraint is this, so this numbers here, okay, must be less than or equal to these numbers here. Then you add, and then these numbers here must be greater than or equal to these numbers here. Okay, then you add these numbers here must be greater than or equal to these numbers here. And then you have this xij and yjk are, xij is binary, I mean integer. Xij are positive integers, put it in here, integer. And then yjk is also integer. Okay, all right. Now we click this one here that says that they are non-negative. We want this because there's no such thing as negative cake slices. Okay, and then you click solve, and that should give you an answer. Here we found the solution. Okay, so let's look at the solution. As expected, what do we see here? Nothing should go from 1 to 4, right? Okay, we are not going to say that nothing should go from 1 to 4. We just simply said there can be going from 1 to 4, it's just that it is too expensive. And so the computer said nothing should go to from 1 to 4, right? Now, originally here, we see that nothing should go from 3 to 7 and from 4 to 5, yeah? So, as expected, from 3 to 7, this is the solution. And then from 4 to 5, it's nothing as well, right? Okay? Just see that the ingenious solution that we have by simply putting a prohibitively high cost that will make the computer not choose it works, okay? So, what happens if you put a cost that is not high enough? Let's just say, like compared to 0.3, 0.2, you put a number, let's say 1, but 1 is not high enough, yeah? Okay, so it is possible that these numbers here will not be 0, yeah? So if that happens and then, you see that it's not 0, so that means that the number that you put here is not high enough, so you jack it up a little bit more, yeah? Maybe multiply it by 1,000, okay? When that happens, then you are going to really force the computer to not choose it because we're trying to minimize the cost, okay? Right. This concludes our session for today.